All right, let me start by saying that I'm just presenting ideas. I am not presenting anything as the only solution. So this video has to do with optimizing tactile and motion systems together. And at least this is the compromise I'm working on. So for starters, when you add a tactile system to your rig, if you want to get the most out of it, you want to isolate the contact points. So typically that's going to be your seat and your pedal deck. Those are the parts that you feel while you're driving. You've got force feedback and you want to feel the effects in those parts. And in order to make the transducers more efficient, if each of these pieces is allowed to move separately, instead of trying to move the entire rig, and mine's, I don't know, it's approaching 400 pounds at this point. That's a lot of load for a transducer to try to move. It just doesn't have the oomph to do it. You'll feel something, but you in no way maximizing what you can get out of your transducers. So with a localized lighter area, the transducers don't need to be maxed out. You can run them at a lower volume. And because you're running at a lower volume, there's room for multiple effects to coexist without drowning each other out. So this is the key advantage to using something like these. And if you see over here, you can see the donuts. And that has a blue spring inside it. This is a weaker one. This is a stouter spring. And even though this feels rigid as heck if you try to press on it, if you're using something like a butt kicker LFE or a butt kicker CT or a TST 329 or 429, anyway, they can easily allow you to feel vibrations while still being semi-rigid. Now, the issue that you run into is that when you're isolating these parts, that does allow them to move and they can potentially rock. And specifically when you're applying brakes, they could flex away from you. And with a motion system, when it's moving you around, the springs will absorb some of that motion. So what I'm looking at in my solution is the use of linear bearings. And I had a video a while back where I first put these linear bearings on my pedal deck. So the entire section above this line is sprung, but there's this long linear bearing with a stout piece of 40/40 bolted in here that keeps it from moving around vertically and from side to side for that matter. And that reduced the brake flex that I was seeing in there. But what I hadn't done was come up with a solution for the seat. And the sad part about this is I weigh a whole lot more than this does. And when, a body's in motion, it tends to stay in motion, et cetera, et cetera. So if the rig is trying to move me around and there is some flex available, I'm not going to feel as much motion sitting here with an isolated seat plate like I have here than I would if I was just bolted straight to the frame. So in this video, what I'm covering is basically the other half of this solution where I'm putting linear bearings underneath my seat plate. And if you look, I've got, I'll add a snippet of this, an earlier video when I'm in Dirt Rally 2, and I'm having a good time and it feels good, but you can see that the seat is rocking around a little. And more than that, it's not just rocking, it's rebounding, and you can actually see that, it's not just like it's rocking a little bit. I'm sure it's hitting harmonics and various other things. So if I'm bouncing around in it, it's absorbing a whole lot of that motion. And I'll jump a little to the punchline. This is complete. I have tested it, and the effects feel better from my D-Box in terms of when I'm moving, I feel more direct. I feel like the effects are quicker now with the linear bearings in place than with the seat plate just sprung. Now, There are other things people can do with this. There are some people with static rigs, and they still sometimes want linear bearings just for brake flex. And in their case, when they're not dealing with heave, they could actually go to an even lighter spring so that they can feel more effects because the entire rig is not in motion. So some people will go in that route. And there are some people who have tactile rigs that have no motion, and they have isolation, and they have the entire rig also on springs, and they have transducers and exciters all over the place. And what I'm covering right now are the big transducers, your BK LFEs, your TST 429s. So when you've got these larger transducers, you typically don't want to mount them straight to a fiberglass seat. So we have a steel metal plate underneath this, and they mount to that because they're very powerful. And this gives you a standard way of doing that. And so my solution is made to fit what was formerly sold as a race base seat tactile plate. So there's no drilling required. It bolts in to the slots on the top and then comes in from the bottom. And I will be sharing the DXF files for that plate. I'm not trying to sell anything. And so if anyone is interested, I'll have a complete parts list, and you can order whatever you want. And if you want to make them yourself or have somebody fabricate, send, cut, send, whatever, you can have them built up for you in that way. Anyway, let's get to the design. This is a Fusion 360 model of a SimLab P1/P1X chassis at the bottom. And it's showing the race-based tactile plate on the left, and something I recently designed for some people with the SimiCube pedal decks. For some people who've looked at the SimiCube product, you might realize that there are tactile effects built into the SimiCube software, and that may be redundant with the tactile isolation that we're using here. But the Sim Hub effects that we have are a lot more mature. SimiCube is still adding new features, and it's really good stuff, but we still have some people who want to have the existing tactile. So this plate has profile plates that bolt, or has two pieces of profile that bolt to the plate, and has room for a BK LFE or CT100 and a TST, and then the SimiCube will line up with these profile slots to bolt to it, and then it's suspended by 4 springs. We're working back here for now, but the key thing is there's 4 springs, and there is some rocking. And in fact, I noticed it was more side to side than it was front to back. Front to back is going to be primarily braking. So let's look at the underside of this. This is the solution that I'm looking at. There's a plate that through bolts to the profile on the top. So you can see here's 2 bolts. On this bottom one, you can see the slot showing for the profile up here. So there are 2 bolts they're going straight into that profile, and then 2 more bolts are going into the slot. So there'll be 4 bolts total holding this adapter plate to the tactile plate. And then on the other side, the adapter plate is chamfered so that the 4 bolts that are going into the top of the profile and bolting to these corner braces won't hit the bottom of the tactile plate. So this allows this part to be very solidly bolted to this plate. Bolting this to the bottom will also greatly increase the stiffness of this plate so that the only potential flex would be near the end. So you can see that the slot is off just a little bit on each side, but that should work. And this is the final version of this plate. And the slot runs the entire length of this slot, so it doesn't matter where your profile is sitting on the slot, which adjusts side to side in order to handle different widths of seat bases. So these could be further on the outside of the slot or on the inside of the slot. And if they're on the outside, then you put the second bolt on the inside. At any rate, it should bolt straight up without any modification to that tactile plate. And this is what I've got on mine right now. I've got the BK in the back and the TST in the front. So that's currently how my system is set up. And these are off-the-shelf 80/20 linear bearings. I'll include the part number and a link in the description below. And this is the 4080 profile. And I got these a little longer than I needed to. So what I ended up doing is, where I mounted it is, let me do this here. I will say this. Now I want to move this and the bearing block. So I've actually got this mounted higher, and that allows, there's still plenty of room for it to move up and down, but it puts this closer to the plate, which should hopefully reduce motion more than if it was at the bottom. There are linear bearing blocks that would extend 40 millimeters below the bottom of the chassis, and a longer piece would work with that. I think this is a good choice. It's middle ground. There'd be more friction with a longer bearing block, but it might offer more stability. These are all experiments. So at any rate, so next I'm going to 3D print these plates and test fit to the underside of my rig, just to make sure before I go to aluminum that everything's going to fit properly. And then once I do that, I'll actually build an aluminum plate out of 60-61 3 or 1/4 inch thick plate, or 6.35 millimeter thick plate, and then I'll mount that up, and then I'll test it, and we'll have some video showing how that works. Okay, my 80/20 package just came. So we've got our new toys to play with. One of the things the 80/20 linear bearings come with are shims that you can put in if you need to, if you have any wear, need to adjust for any additional gap that you have. And in this case, I think we're mostly going to be waiting for it to break in. So that shouldn't be an issue. So let's see how this goes. All right, so this is sort of what we're going to have under the seat. As the linear bearings come out of the box, they're a little bit loose. So if you take this one, this is how it comes stock. You can see there's a lot of lot of play in there. Now this one, there we go. This one, on the other hand, is not that loose. It slides freely, but it doesn't have a lot of play. So this should work really well. But like I said, as it comes out of the box, you have to adjust it some. So in this case, I'm going to say there's, I don't know, about a millimeter plus underneath these guys. So the way you adjust these, you don't take them off completely. You just loosen them a bit. All right, just like this. And then you take these. I'm going to start with a couple of them over here. And they're in these peel-off blocks. So these are good for, they say there's like 15 of these little shims. And for what it's worth, a single shim is only like 0.27 millimeters, 0.26. So I think it's probably supposed to be a 1/4 millimeter. So if I take a couple of these, oh, let's see, I thought I had, yeah, these are just singles. So a couple of these will be about 1/2 millimeter, and I don't think that's actually going to be enough. I'm going to just go ahead and get a couple more, get up to at least 3/4 millimeter. And then I think that'll give me just enough thickness to take out a bunch of this slop. Okay, all right, so we got that in, and then we tighten these back up again. And it helps to have this thing in there just to make sure that when they're tightening up, they're tightening up properly. There we go. I may have. Well, let's see if this, if they get a little better when I tighten them up and it pulls them in tight. All right, so there we go. That's better. So now I don't have nearly as much play this way, but I still have play the other direction, and I can loosen up the ones on the side and do the same thing there. So I'll just and if this is like the first one I did, it'll take a couple of these on each side to get it right. We'll see how this goes. So I'll put this back in here. And then do the other side. Actually, let me see this. This is actually kind of snug. I think I might need to, there we go. I think I got the alignment a little off when I tightened it. Now in use, they'll shift until they are right. Get those in. Yep. This. All right, so all right, let's see what we got here. Should be all right. See, I'm getting about 6. Okay, 6 or 7. So right now, the plate that's fitting inside of the tactile plate inside of the chassis has, I think, about 5 millimeters of space on each side, but I'll need to verify that. To put the threads in for these. So these are going to need threads so I can bolt them in, and that goes pretty well. I got this this threading tool, which is a little different than some of the normal ones that you have to rock back and forth. Let me get one of those. Historically, I've used a tap that's like this that has the 4 flutes in it, and you typically work it, you crank it in about halfway, go back half a turn or a quarter turn, and you work your way in, but you have to keep breaking the pieces free. And this is a spiral threaded tap, and it's designed to just be driven straight in without stopping, which is great. So you can get a good deep thread without taking a million years. But let's see how deep this is. Looks pretty deep. Now we'll probably want to use deeper bolts than this, and I've got some that run quite a bit deeper. Let's see. The only thing I need to do after doing a test fit using the 3D printed piece that I've got here is to take some of these pieces of aluminum and fabricate them to fit, and then I'll be able to test it. After shimming the linear bearing, I bolted everything up to the 3D printed mock-up of the final metal part that I'll be using, just to make sure that it fit perfectly before going to metal. So after jacking up my rig and making sure it was solid and safe for me to climb around underneath it, I secured the 3D printed test plate to my seat plate, bolting here through into the profile that hold my seat brackets, and then putting the bolts in from the top that go straight through to the tactile plate itself. And I need lock nuts on these. And what you'll see next is when I put the linear bearing on, I realize that I have enough clearance to mount this to the top 2 slots versus the bottom 2 slots. So the profile is longer than it needs to be. So I reposition it up a little higher, and that's where I ended up putting it. So there's less of a less room for anything to be multiplied. Getting these things lined up was a lot of fun, especially when you're hanging out underneath your rig. What's nuts in this video is that once I got it secured, I scored the 3D plastic where I thought I could drill holes to avoid slots, since I don't have a milling machine at home. So after the initial test fit, I created some jigging. So this is a punch plate. It's made to fit my punch, so I can just center punch where I'm going to drill the holes to make it easier to fabricate. So I'll 3D print that, and then I'll start going to aluminum. I have to say, 3D printers are just amazing. I can't imagine doing some of this work without being able to very quickly generate templates to work from. What you can see with this punch jig is that it's just great aligning up all these holes and making it real easy for my center punch to fit. And as I'm building all of this, I'm trying not to bore you. I'm only spending, a short period of time on each bit, but I wanted to include all the steps just so that you could see what was involved in fabricating one of these plates by hand. It doesn't require a huge amount of equipment. The two biggest things that I'm using in this are a small bandsaw with a metal cutting blade and a drill press. I have a larger bandsaw, and I actually have a metal cutting blade on my table saw. If I had, if these needed to be precise 90-degree corners, I would have used my table saw instead of using a bandsaw, and I wouldn't have nearly as much to clean up on the belt sander here if I had gone that route. But the setup time to pull out my table saw is just, for this it was easier just to use the bandsaw to make 4 simple cuts, and then this is hidden, so having perfect 90-degree edges didn't matter. The key thing is that the bolt holes were precise, and that's all that really mattered to make this work properly. Now, when drilling this, so the punch holes are good. You'll see I'm doing a little hunting and pecking, just aligning up the tip of the drill bit with the punch hole just to make sure that the alignment is good. And then I'm using some cutting fluid to make sure that it doesn't dull the blade or the bit, and it also cuts freely. So, and you'll see I'm chipping away at it to make sure there's just small little chunks of aluminum and no long strands binding up on the drill bit. This is a fairly ancient drill press, and it's not precise by any means. And even though I've got a full mill and lathe and other things at my disposal, my makerspace, it's just so much more convenient to do things in my shop. So I'm just using the tools that I've got, which is plenty to make this work. So it's not a huge deal. It's surprising how little you can get away with to make something that's fairly precise, as long as you can get your holes right and get your alignment right. Use decent drill bits. Just about any drill press will take care of things. Now, there are a few other tools that just make life a little easier. This is a circle cleaner. There's another point where I'm using another one of these metal edge tools, and I honestly don't remember the names of them now, but this is just cleaning up the burrs around the edge. A deburring tool, that's what I'm thinking of. So there's a deburring tool thing coming up where I'm just cutting the edges off, but the whole deburring tool is just really easy to work with. With a drill press here, they're out of frame. There are markings where I can set a depth for this. So the depth gauge is set so that I can get the bolts just below the top surface of this plate, so they're not rubbing on the tactile plate. And that works pretty well. And there's a lot of surface area going on with this large bit here. So it's good to use cutting fluid for something like that. Now, one of the things I thought when I got the holes measured from where I scored it underneath my rig, when I test fit the plastic part, that I'd be able to line it up, but it turned out that didn't work. Going back to this, I'm just finishing with my random orbital sander. You can take just 200 grit sandpaper, and if you go lengthwise, you can get a nice looking brushed grain if you want that look. I like this for something no one's going to see. I'm mostly just making sure there's no sharp edges. And here's the deburring tool that I'm coming back with. So The key thing is I don't want the edge of this plate cutting into the powder coat on the underside of my tactile plate. So I'm just making very sure that there's no edges. I also went back to the belt sander again, which I didn't bother showing in this video. And here's a sander that I use for a lot. I've got a couple of these with different grits of sandpaper for woodworking, but once again, if you can just run it the length of a face pretty uniformly back and forth, you can get a really nice grain finish for something that actually shows if that's what you're after. But finishing is somewhat optional on this just because it's hidden. I tried to test fit it using bolts, but apparently when I scored it, I wasn't accurate enough. And realistically, you need some play in order to get the linear bearing alignment right, or it'll bind. So I needed to go back and create slots for the two holes that need play, the two holes that go into the profile for the seat brackets. So those are at a fixed offset to the chassis inner wall. And so there has to be some sliding in the plate to allow for that, so I can get the linear bearings to be well aligned and not binding. So now we're actually building this. So this is the final version that'll be mounted to my rig. And spoiler alert, it fits properly with the slots. So this is going in. Now, one thing you might notice if you saw the earlier part of this video when I was putting threads into the profile, I did end up using the much longer bolts that are about 30 millimeters deep. And I did use cutting fluid, and then the spiral tap was able to go deep into the profile. So there's a lot of bolt inside the profile here. You'll see I'm tightening things down pretty hard as well. So my hope is I never have to pull these apart, or that they stay together as long as I want them to. The lock nuts should help. There's still no guarantees though, but it should work well. Anyway, here it is. We'll see how it looks in the rig. So this is the final installation. I'm starting with the outer bolt holes, and I'm going to tighten it up flush but not tight against the tactile seat plate. So the idea is that I get it parallel, and then when I put the linear bearing on, the linear bearing slides on, and that sets the linear bearing where it sets where it should bolt to the side on the chassis. And then once I've got the linear bearing snug tight against the chassis, then I tighten the top plate so that it's still lined up. The key to making this work is to prevent binding, so that earlier on we talked about setting up proper shimming, and after you get the shimming right, you have to get the alignment right. So this needs to be at 90 degrees, and before starting, the tactile plate needs to be level. So you want to make sure that you've got your spacing for your springs right, and you want to go around your rig and make sure that your plate is parallel to the chassis. If it's at an angle, it'll bind. So this will help hold it perpendicular to the side of the frame once it's set up. But until that point, you want to have everything as square as possible to make sure the alignment works. But once you've got the alignment right, then you can snug this down and it should be free sliding, and ideally it won't bind on you in use. And I'm torquing this down pretty well, and this will be the end of the build here. I'm not going to waste time showing the other side. It's the same. And the next thing I need to do is some testing. So on to that.